about just turning it like off, just off, other way, basically. So we'll see what happens. Maybe next time I'll have a chair and stuff I can sit on, and I'm sure there'll be some improvements. Well, welcome to EE102. My name is Stephen Boyd, and I'll tell you a little bit about the class. It's probably not a whole lot different in format from 101, but I don't know. We'll go over that quickly, and then we'll just start in on the lecture and stuff like that. So let's see. I'm sure this won't work, but can you go down? Can you focus on this? Let's see. Everything's going to be sort of interesting today. Hey, look at that! Amazing. Okay. You might want to zoom in a little bit here, and I'll just go over. Let me just go over some of the basic and boring stuff first. There's, I guess there's 3 lectures, and then there's a section. The section time and day has been fixed. It's Monday at 7 o'clock, and we're very close to getting a room. This is probably a good time for me to mention all real information about the class is going to be on the web page. So everything will be on the web page. So don't ask. Anything printed is probably out of date, but the web page is not. So that's where you'll find out, like, for example, where the section is and so on. And in fact, I suppose it's likely that we're going to get a room, right? So we may in fact have a section on Monday. We will. Okay, so there we go. We'll actually have a section on Monday. See, my name is Stephen Boyd, and you look on the web page to hunt me down. You can find me. I guess my office hours would officially be sort of after class on Mondays. And I guess we're going to have a Wednesday cycle for the homework. So that's it's sort of planned that way. And then there'll be some TA office hours also around then. Let's see. Our TAs are, I guess you all know Jessica Lang, I guess, from 101. And also Leo DiCarlo is going to be the second TA. So we're very, very lucky in the TA department this quarter. And we'll be figuring out office hours and locations for them soon. Maybe today, I guess, the usual chaos of the first couple of days. And then, needless to say, that information will be on the web. That's where everything will be. Oh, and I guess along those lines, I guess you should hurry up and register for the class or whatever, because I guess when you do, it increases your quota. Although, in fact, we won't be putting any demands on your quota. I don't know. It's a bonus if you're dumb enough to sign up for this class. Your quota will increase or something like that. But then your print quota, I guess that is serious. That also gets bumped up. And although we'll bring copies of the lectures and all that kind of stuff to class, and we'll make an attempt to kind of keep extras of them available near my office. Your best bet, as usual, is the web. Printing handouts and things like that. Okay, textbook. So let me just say a couple things about textbook. Most important point about textbook is there isn't one. We don't have one. The lecture notes are complete. They're probably a little bit less than, maybe we'll write up some other notes or something during the quarter. I claim that they're actually complete. So many people go through the class. They never ever look at a textbook and things like that, and they're just fine. They go on to lead reasonably normal lives and all that kind of stuff. If, however, you really need to have a textbook, you're welcome to go buy one. And the good news on the textbook end is that all the books are the same. They look different, right? But in fact, the topics are identical. A lot of them they're kind of boring. They're usually 1,100 pages, and they just have kind of everything is there. And you might, depending on, how you feel about this, every now and then you could just go grab a textbook and see what they're doing. But all the topics we cover will be in some textbook, but it'd take you so long to find it. There's no point really worrying about it that much. Okay, so we'll have a couple of textbooks on reserve at Terman, and every now and then you might want to look at one. So I guess also I'd appreciate feedback on issues like if you find one section of the stuff we do, if you find the notes actually aren't adequate, that'd be a very good thing for for us to find out. So, okay. You guys are lucky. We're finishing up all the boring stuff right now. All right, so the course requirements, I think this is similar to 101, but I'm not completely sure since I didn't do 101. But I guess we'll have weekly homework assignments, including one today is there somewhere. And we're also going to have, I guess, these short quizzes pretty much every Friday, except not next lecture, so not the first Friday, not the last Friday, and not when we have a midterm and all that kind of stuff. So I think it works out to about 7. And the quizzes, I guess you did those in 101, yes? You did 4. Okay, so we'll probably do this a little bit more religiously. And I don't know, I think they work pretty well. It's a good way for us at the end of every week to say, here's a simple problem we think you ought to be able to just do just like that. Okay, and it's nice because you know, you're perfectly welcome to like just look at a quiz one day and say, I had no idea, never saw this before in my life, that kind of thing. And it's a kind of a low stress situation. And it's good for us, you know, when we give you back a quiz and you have like a 2 on it, it's great because it's a message from us to you that here's something that we think is kind of basic and you apparently didn't know. But on the other hand, this is not a career ending. This doesn't terminate your electrical engineering career. So I don't know, it seems like a good thing. But, there's a midterm, and we've even set the date. It's the 5th week of classes. So what that makes it is it's going to be in your distribution of midterm times. We're going to be sort of at the beginning, I think, right? Because the way it usually works is people start thinking about the midterm the 6th week, and then a lot of them actually spill into the 7th because people look up like during the 6th week and they say, oh no, we should have a midterm, and then they realize they actually haven't covered any material yet, which is and then so they have to cover some material quickly so they can have a midterm, and you know all this, of course. So I think we're going to be on the early end of your midterm distribution, and there's a final, of course, at the regularly scheduled time. Also, I guess tapes of the class are available are going to be available in Termin. And I don't know how many copies they'll have, but you're not, you know, I guess some people, you know, can't get up this early or something like that. And so I don't know. But if it gets depressingly empty in here, because like no one can basically make it in at 9 because it's just too early, then I don't know. We'll do something about it. Like I might insert something like deliberately insert something confusing in each of the tapes, right? But I'll tip off the people actually here in person, and our remote SITN students, of course, that what I'm saying and is being recorded is nonsense. So that's just that says you should stop in on the class every now and then. Even though. Of course, it's very nice to have fast forward abilities, which you don't have during a lecture, but oh well. Okay, I think that kind of covers the mechanics of the class. Are there any questions about how it's going to work? There's a lot more details we could go over. It's kind of boring. I don't know. The prerequisites are pretty simple. EE101, basically. And in fact, technically you don't even need that because only the circuit background, this is sort of different from the circuit background. So it's, okay. Any questions? Okay. Maybe I might say a few things about where the class fits in all of electrical engineering. I don't know, should I do that? And then we'll start in. So this is it's one of your basic classes, and what it really is we're moving up the abstraction chain from 101. So in 101 you look at circuits, you look at resistors and capacitors and transistors and interconnections and things like that. And in 102, and I guess this is the way everything works these days in computer science, electrical engineering, everything, you sort of move up the abstraction ladder to a higher level, and that's in fact what signals and systems is. So we'll talk a lot about signals and systems. This is both the abstraction level is actually both the power and it's also the tricky part about it. So it's tricky because it's abstract, because we'll no longer be talking specifically about voltages or something like that, although many of the signals we'll look at could very well be voltages in a circuit. The power is actually amazing, because the stuff we'll do will apply equally well to, for example, understanding how a car suspension works, and also understanding how an ultra-fast interconnect on the fastest generation of computers works. The time scales are off by factors of 10 to the 10, and the physical scales are different. All the variables are different. In one case it's mechanical, in another it's electrical. But it's actually kind of amazing that even at this first level of abstraction above the basics, it's the same. It's kind of the same. It's neat. So we'll see. I don't know. That's an introduction to where the course fits in. I could tell you where the material's used. It's used. It's basically used throughout electrical engineering, but in a lot of other fields as well. In mechanical engineering, something called automatic control, feedback and automatic control is based on the material some of the stuff that we'll cover in this class, and a lot of other fields. So maybe that's enough of these vague things, and we'll actually start on the lecture, unless there's some question or something about how things are going to work. I guess since a bunch of people were coming in, well, actually, according to me, on time. I think we started early, but let me just say, actually, the only important thing I have said, actually, in the last 10 minutes, is that all current information is going to be on the web. So anything you get printed could be out of date. So just go to the web. All right. So we'll start with our first lecture, which is on signals. And so we'll just spend some time talking about what signals are and stuff like that. In fact, a lot of the course can be approached and sort of taken as just a math class. Now, the disadvantage of this is that it is boring. So this first lecture is basically going to explain just sort of what are signals and things like that. In fact, it's not that important. I mean, the things you really have to do is kind of the math course style stuff, which is sort of mindless manipulation and things like that. But so this will actually explain the background and the meaning and stuff like that. So we'll start with I don't know, a definition of what's a signal. Well, it's a function of time. That's what it is. So it might have a symbol like F or something like that, and that might represent the force on some mass. Now we have to talk about a couple of things here. It's a function, and so what that means, when you write down F, it means it's a function, and you pass it an argument, which is the time. So for example, f of t. Okay? F of t, the function returns a value. Okay? So this is the computer science model of what a function is. It's not, if you say f, well, if we're doing statics, in that context, when I say f, I mean a force, and someone say, well, what is it? You'd say, well, it's 3.3 newtons. That's what it is, or something like that. In the context, if f is a signal, and then I say, well, what is the force? Someone says, well, I mean, when? That's the next question you have to ask. Then you say, oh, well, at t equals 1.15. And then they say, oh, well, at t equals 1.15, the force was 5.6 newtons. Okay? So I don't know if that made any sense to anybody, but basically what I'm describing is the data structure associated with what a function is. It's a complicated data structure. So often these will have symbols that are supposed to remind you of what you're talking about. For example, F might be a force on some mass, or you might have V out is the output voltage of some circuit, or P might be the acoustic pressure at some point. And there are some conventions which you'll quickly see. We won't explain them to you, but you'll sort of see. Some signals are often associated with inputs, things like U and V and things like that. Other signals like Y and Z are often associated with outputs. People like to use letters sort of at the end of the alphabet sometimes to denote signals. These are just pure conventions, and doesn't mean anything. Okay. So if someone says, well, I'm thinking of a signal P of T, and I'm thinking of a signal P, and someone says, well, what is it? There's many ways to describe it. One way is I could plot it for you. I could say, well, here it is. It's this. This is an acoustic pulse. That's what this is. I measured this using a microphone or something like that. And it gets to a peak of about plus and minus 1 newtons per square meter, or pascals. So that's an acoustic pressure. And this is what it was. So for example, I could ask everyone here, what is P of, I don't know, minus 1? So what's P of minus 1 here? Yeah, 0, right? And to do that, someone looked right over here and found it was 0. And I could ask, what's P of 1 millisecond? And the answer is about minus 1 Pascal. Okay? I could also ask, by the way, what is P of 5? And what would be some reasonable answers to that? 0, okay. And then suppose, a lawyer was present, what would you say? Suppose someone really, who was really going to hold you to every detail. What would you say? Yeah, that was it. I heard someone say it. Yeah, we don't know. Yeah, that's it. Yeah, so if someone was really a stickler, you'd say, P of 5? I don't recall. No, you'd say, we don't know. But a normal person, if there were just engineering and normal people around, you would say, it's 0. And someone says, but it's not shown. And you'd say, yeah, but we assume the person who made the graph wasn't a moron. And so the presumption is then that they wouldn't have shown you this little bit claiming this was P when all sorts of interesting stuff happens outside here, right? There's kind of a presumption there. No, we spent more than enough time on that. Okay, so actually, let me just mention one thing here, which is actually a very good thing to know. And it makes you look more or less sophisticated. And it's if you have just even a slight minimal background in computer science, it makes perfect sense. A lot of people, when they want to describe a function, they write it this way. Okay? Technically, this is wrong notation, and not only that, it can even lead to confusion, right? The correct thing is if I say I'm thinking of a function, the correct way to write it is I'm thinking of a function P. Now the symbol is ambiguous because you don't know, is P a constant? Is it 3 or 4, or is it a whole function? But this is exactly like any real computer language. It's exactly the same. You see a bunch of ASCII characters, and you don't know if that's a double or some unbelievably complicated double data structure, or whether, for example, this thing here, when I write down P, like in C, for example, that could be something complicated, like a pointer to a function, or it could be a function, and you don't distinguish it any other way. Okay? So please, please, please try not to say, I'm thinking of the function P of t. Now, having said that, people do often do things like, oh, I'm thinking of the function cosine t. Okay? Here it's okay because you're kind of, this is the pedantic way is to say, well, I'm thinking of a function f. And someone says, okay, well, what is f? And you say, well, f is defined this way. F of t is cosine t. Right, so that's the distinction. So, and by the way, this is universal in all the books you'll find, and it's just totally confused, right? So the way to do it is to actually turn on your careful parsing mode, and just think about it. Because if we all here know that p is a function, and I say what type of data structure is p, what's the answer? It's a function. Okay. If I say what is p of t, what is the data type of p of t? What's the answer? What would it be? This is a C program. It's what? It's not a function. T is presumably some real number, something in the domain of p, right? So p of t would be like sine t. This is in C this would be a double, right? It's a double. It's what p returns. It's the value of p. So there's actually a big distinction in if you were programming, you would never confuse p and p of t. They're totally different objects, right? And so I think here it's going to make less difference because we're not strictly, we don't have people strictly parsing what we say and stuff. But it just makes things clearer to bear in mind the real difference between a function and then the value returned by a function. Okay. So let's look at some attributes of signals. One important one is its domain. And the domain of a signal is the set of arguments that you're allowed to pass to it. Okay? So that's what it means. So some common domains would be basically all real numbers. So for example, if P is a pressure, an acoustic pressure like that, we are allowed now to ask or query what is the pressure at any time in the past or the future. something like that. That's one option. You might be interested in basically just non-negative values, or just some value after some starting point. This would be the case when you're not interested in what the signal was doing before. You're interested in how what happens to it in the future. This is quite common. In fact, a reasonable fraction of the course is going to concentrate on this. Okay? Where our real interest is going to be how something evolves or works in the future, and not particularly, not that much on what happened to it before it got into the current state. So that's going to be one. Another is it might just be in some interval. This would be the case, for example, if you take some real measurements and you turn on and start recording a voltage or record an acoustic signal with a microphone or an accelerometer and some mechanical system, and you record it over some interval. What would happen then is you wouldn't have a picture that looked pretty like this. It might end with this thing wiggling. And then there would be the common sense assumption. Then when someone says, what's the value of this thing at t equals 5? Then the correct answer would be, I don't know. We stop measuring at t equals 3. That would be the correct answer then. So, okay. Now another thing that we won't see too much in this class, but you'll certainly see in 103, in fact it's the entire basis of 103, is that you can have a signal which is actually only defined at uniformly sampled points. Okay, so this is, in fact, more and more of the world works this way, and the good news is that everything you learn in this class transposes and extends immediately to signals which are uniformly sampled. So I'll give you an example. Everybody here has a CD player and stuff like that. Does anyone know sort of the format of a CD, of this signal on a CD? No. Interesting. Oh well. Anyone know what it is? What the format is, or how? Huh? Yeah. Okay. Yeah. Actually, on the CD, it's just little pits that are either there or not. But eventually, after a long string of other transformations, it becomes a sampled version of an acoustic signal, and it's sampled 44,100 times per second. That's what it is. Okay. Now the idea there is it's fast enough that if you kind of just draw a nice smooth approximation to it and then play it through an amplifier and speaker, we all hear it as perfect, as a perfect reproduction of the original signal. Okay. So that's an example. So that would be a signal, an example where if you we'll actually talk a little bit about this, but it means that technically speaking, the digital output from a CD player is a signal. It's a representation of an acoustic pressure, but it's only given at integer multiples of 1/44.1 kilohertz. Okay. Something related to that is a so-called discrete time system where, in fact, you abstract away. There's not even any time. In fact, often here, T is called, to emphasize the fact that it's not necessarily time, it's called an epoch is one, or a stage. So for example, in areas like economics or finance or something like that, where there's multiple events or investment periods, then you'll simply refer to time, T, as 1, 2, 3, and you won't say what they were. Maybe these are investment periods, maybe they're equal in time, maybe they're not. These could be business days, you don't know. Okay? So in this class, we're going to study signals that are defined on reals, mostly, and often non-negative reals. Okay. Okay, so this is really, if you think of a signal as a function, the domain affects, proper way to think of that is to think of what are valid arguments you can pass to the function. Okay. Now, at the other end, you can ask what is the data structure, right, or the data type of what is returned by the function. And these are the issues we'll address now. These are usually not addressed. Okay? So for example, you can have physical units of a signal. For example, volts, milliamps, meters per second, anything, dollars, doesn't matter. Okay, these are the physical units of a signal. And of course, sometimes doesn't have any. And in fact, a reasonable fraction of our course is going to take place without any physical, there won't be physical units. And that'll be both confusing and a huge advantage. Because it'll be confusing because, well, you won't be able to easily picture something like an integrated circuit or a mechanical system or something like that. The advantage is the same thing, that what we're talking about now applies both to integrated circuits and to mechanical systems, and to an airplane control system and all this kind of stuff, right? So, but it's good every now and then to think about this. So you also have the dimension or type of a signal. For example, a signal could be real valued, which we often call a scalar signal. And there, U of t is just a real number. It can also be a vector signal, like it could be, this could be a vector with some dimension, 5, 10, 5,000, or a Boolean signal. That would often be the case, for example, in a digital system or some kind of communication system. And here the signal is either 0 or 1. So it's a real number, but it's, so if you like, in terms of computer science, you just think about what, I mean, here we're actually just describing what the data type of the returned, of the returned value is for the function. That's what we're describing. Yeah. Oh, just out of curiosity, how many people understand what I'm talking about when I say that? Because I'll shut up if the answer's like just a handful or something. Well, okay. So we're going to keep going with the C analogy, or? Yeah, so wouldn't call that an overwhelmingly positive response, but we'll just. Actually, I think we quickly don't need that anymore. All right, we'll get beyond that. We'll just move to the higher abstraction level, and everything will be fine. So, for example, I mean, here would be an example. I could say, well, I have this vector valued signal, and what happens is V is a signal here. So actually, this is fun just to figure out what it means, just to work out what it means. So if I walk up to you and I say, what's V? Well, it's a signal. And in particular, in this case, it is a function taking as argument a real number and returning a 3 vector. Okay? This is a complicated object. If you're confused, that's normal. Okay? This is a complicated data structure. So for example, I could ask you, what is V of 7.5? What is the data type of that? What is this return? What do you get? What does this evaluate to? It's a 3-dimensional vector, exactly. Okay, and I could ask you, what's V2 of 7.5? 2 here gives you the subscript into the array, or the what's that? What type of object is this, or what's the data type of that? It's a scalar. It's a real number. It might be, I don't know, 3.2. It also might have some units attached to it. Like someone say, well, what are the units? And the answer might be nanovolts. But we didn't say. And often we just won't. So, okay, that's just a quick example. Okay. So we should look at some common signals that have names. And these are good to know about. Let's see. One is you can have a constant signal, and other names for that are static, as opposed to dynamic, or DC. That's a great term. It means direct current, and it's a retro term, is what it is, right? So basically, if you say that, electrical engineers in their 80s and 90s will know exactly what you're talking about. But it's kind of cool also to propagate it. It has kind of a retro feel. I like it for that reason, because it irritates people who are under 80 and stuff. So, okay. So this is a constant, and this is very confusing. I mean, basically what it is this. So U here would be a function, and you can pass it an argument. But no matter what argument you pass it, it returns the same thing, which is A. So then, once you kind of get past all this, you can start. You don't distinguish between it. You just say, well, it's a constant, or is it a function and stuff. But if you're in strict parsing mode, it's not a constant. It's a function that no matter what you pass it, returns a constant. Okay. The unit step signal, and this is defined this way. It's a function which is 0 whenever t is less than 0, and then bumps up to 1 for t equals 0. So this, you're going to see tons and tons of times. There's a sort of a plot of it. Looks something like that. And some books use some notation for this. One is U of t, is one notation for it, for unit step, I guess. 1 of t is another one, which is this. I like this one because it's kind of suggestive, but it's a little, it's getting a little bit dangerous there. Yeah. I don't know that we have a fixed notation for it, so I don't know. Maybe somewhere in the class we'll on an emergency basis, need to bring in bring in some notation for unit step. But these are some symbols that are used. So one in U. Okay. Another variation on that is like the unit ramp signal looks something like this. And the unit ramp signal goes up to here. It's continuous, and then it goes up linearly after t equals 0. That's the unit ramp signal. Oh, so I should mention a couple of things. Where do these things come up? Well, unit step signal might be an idealization of the voltage you would see in some digital circuit, for example. It's kind of a boring circuit because it's got state 0 up to time t equals 0. Then it makes exactly one transition to 1. But, I mean, if you assume that all the exciting stuff happens within plus or minus 10 nanoseconds of it, this is not a bad approximation of what the type of signal you might see in a digital system. Well, you can have a rectangular pulse signal. That's something that might look like this. Oh, and I should mention that there's many ways to draw these. If you draw this with this vertical thing drawn in, I think it looks nicer, and it also, especially early in the morning as it is now, it's better for your eye, so you don't right your eye. Otherwise, when you draw it like this, your eye doesn't know exactly. Whoops, your eye doesn't know exactly where to go and stuff. So this is, but you have to remember this is not the riser on this tread here is there only so your poor eye can follow this and visually grasp what it is. Okay, here's a signal that I guess you've seen a lot in EE101, and that's a sinusoid. So my monitor is actually beginning to fade up here, so I'm just going to turn off one, turn on the other. So a sinusoidal signal is one that looks like this. Okay, and in something like this, you have to be very careful about what's what in here. T is the argument of U here. So T is a dummy here. A, omega, and phi. These are called signal parameters, right? Because they're constants that kind of describe what the signal is. So really, what I'm saying here is this is describing a family of sinusoids, right? And then A is the amplitude, of course, and omega is the frequency, and phi is the phase shift, that kind of thing. Okay, so we'll spend a lot of time looking at these kinds of signals, and if you open one of these 1,100-page books, you'll see exactly the same, right? That you'll see piles of pages and homework problems, on and on and on, unit steps, unit ramp, on and on, sinusoid, all that. Okay, very important to understand that, on the other hand, we have real signals. Okay, so real signals are things like an AM radio signal, or an FM radio signal, or a cable TV signal, or the actual signal inside a processor, or inside some digital circuit, or an audio signal, or an NTSC video signal, or an Ethernet signal, something like this. These are real signals. Okay, they're not given by, needless to say, they are not given by mathematical formulas. Signals that are given by mathematical formulas are more or less useless in practice. Right. So then you might ask, why is it when you buy this 1,100-page book called Signals and Systems, and you sort of thumb through it, you will only find cosine and sine and step and unit ramp and so on and so forth. And hopefully that answer will become clear during the course. But it's important to remember that the real applications here do not involve unit steps, unit ramps, sinusoids. They involve these signals here, communication signals and all sorts of other stuff. Okay. So I won't go into the details, but this is sort of the idea. So, for example, an audio signal, here's a microphone here. It's producing a voltage, and we could translate acoustic pressure at the diaphragm here into voltage. That's a real signal. Okay, it isn't given by a simple formula like this. That's a very simple view of the world. It's obviously not, right? It's a very complicated thing. Okay. So we'll talk about a couple of things, like, for example, how do you measure the size of a signal? So it turns out, actually, for measuring the size of a signal, although it's a pretty intuitive idea, like is a signal big or like is an acoustic signal large or small, this is pretty obvious. I mean, you listen, and it's either very loud or it's not, and that sort of stuff. But it turns out there's different ways to describe the size of a signal. And the real shocker here is that they're different. Although, at first cut, they're about the same. I mean, if you scale a signal, they all get bigger, right? But the real shock is that they're actually that these things can actually be very different. So, and whether or not a signal is big or not depends on the application context. So let's take a look here. A very, very common way to measure the size of a signal is to take its integral square. So you take the integral of the square. The square is non-negative, and so when I integrate this, I get a number. Some people call this total energy because, for example, if you were a voltage or a current, wouldn't matter, and I stuck it across or through a 1 ohm resistor, right, then this integral here gives you the total energy in joules that you end up dumping into this resistor, right? So that's the total. Because if U is a voltage, say, and you take U squared divided by 1, you get a power in watts. You integrate, and you get joules. So this is directly in joules, right? So that's the integral square. Now the truth is that the integral square is really, and I'll tell you the real truth, the real reason it's the most common measure of the size of a signal is because we have a whole bunch of methods that allow us to easily manipulate things with integral squares, some of which we'll see later in the class. That's the real truth. Not because in a lot of applications we're worried about the temperature rise in a 1 ohm resistor. Okay? But that's it. So some people take the square root of the total energy, and that's an interesting quantity. Its units are a little bit bizarre. If U is a voltage, then this has it's in volts per square root second. Did I get that right? No. I don't think I got that right. It's integral V. This is integral V squared T. No, it's worse than that. Sorry, it's volts. It's joules. Sorry, it's volts square root second is what it is. If U is in voltage and you take the square root of the total energy, right? Then the unit of this is volts squared. The unit of the integral is volts squared seconds. You take the square root of that and you get volts times square root seconds. Kind of a bizarre unit. Integral absolute value is also often used. Here you're integrating the absolute value of the signal. Peak or maximum absolute value of a signal is very often used. It's also very critical in many, many systems, because in many, many systems, what you really have is a limit not on the integral square of a signal, but in fact it's universal that you have a limit on the voltage of a signal. For example, any audio amplifier that you have has a limit on the voltage it puts out. It's something like, plus minus 22 volts, period. There is no limit whatsoever on the integral of the square of what comes out of your audio amplifier. There is a limit on voltage. There's also a limit on current, but that's another story. So that's really what you have. So therefore, for an acoustic system or something like that, in fact, for any electronic system, this is a very important question, is what's the peak? Because you want to know the maximum value or the peak, because you want to know, is it going to overrun the allowed range? Okay? That's the idea. Okay. Another one is the root mean square value, also very widely used, also just denoted RMS. And here what you do is you take the running integral of the signal, like squared. So that's the sort of the energy in t seconds. You divide by t, and the units of this now becomes something like a power. It's in watts. Okay? Yeah, so you have that. Then you take the limit as t goes to infinity and the square root. You could take the square root before or after. It doesn't make any difference. And this is the root mean square. And so it has the same units exactly as the signal. So if U is in volts, this is in volts. And this is a very, very common way to specify the size of a signal. What's interesting about it is this is across many, many fields. Okay, so this is when someone deep inside an integrated circuit says, this power supply wire has, typically 30 millivolts RMS of noise on it. This is the number people would use. RMS also, by the way, is what a control engineer would say. That's how they would probably, as a first cut, specify the tracking ability of your CD player. They'd say, well, the focus control system there, or the tracking control system, tracks the cylinders on your hard disk or your CD. They'd say, with a tracking error which is about 10 microns RMS. That would be typical. If someone builds an automobile suspension system, people would ask, how smooth does it ride? And the answer would probably be expressed in terms of the RMS value of accelerations experienced by the passengers. Okay, so it's very widely used measure. There's also average absolute value, and there's lots and lots of other measures of signals. And they're often comparable, but sometimes not. So for example, if you have a sinusoid, here's your sinusoid, then the peak is absolute value of A. That tells you that's the biggest this signal gets, the largest value. Its RMS value is, this divided by square root of 2. Its average absolute value is 0.636 times this. And things like the integral square and the integral absolute values, they're both infinity. And I should also mention here that once you have a notion of the size of a signal, it allows you now to talk about deviation between two signals. And you do that by talking about the size of the difference. This is extremely useful. For example, you could ask when someone has, when you have a CD player and you play it, then you could say, well, how well does this CD player and all the associated system reproduce the acoustic pressure? That's a reasonable question. In other words, you have a studio quality microphone over here, you record it, put it on a CD, you reproduce it here, play it through a studio quality speaker, and the question is how close do you do it? And someone might say, well, actually, for an RMS level of this, the error, which would be sort of the actual acoustic pressure minus the reproduced acoustic pressure, might be, they might tell you that it's, I don't know, it's 0.001 pascals or something like that as an RMS level. You'd get that by taking the difference. Yeah?
Is RMS only relevant for periodic signals?
No. No, in fact, for a periodic signal, all you need to do here is integrate over one period, and then you're done. Okay?
But it's relevant for non-periodic?
It's relevant for non-periodic signals. Now, it is possible that RMS doesn't make any sense for some signals. Notice that this limit just simply won't convert, won't exist. That's possible. Okay. So I'll mention a couple other qualitative properties of signals. This is going to play a large role later in the class. Some qualitative properties are things like, well, a signal decays with time. Is that good or bad? Well, it depends, of course, entirely on the application. If U is a signal that represents the tracking error or something like that in some system, then the fact that U decays is good. If U represents the amount of the total value of some portfolio or some economy, then of course this is not good. So, I mean, it all depends on the application. U converges if it converges to some fixed number. Again, that's either good or bad. Is question? Was there a question or? I thought there. Oh, maybe not. Okay. So that's so it can converge. People say it's bounded if its peak is finite. So in other words, if there's an absolute limit on how big the signal is for all time, right? Then you say it's bounded, and the opposite is unbounded. Some people also say blows up, which is kind of a more actually this is kind of, I guess it evokes a certain image, but of course that's good if what you're working out here is the dynamics of an economy or something like that. This is of course good. Well, I suppose if U is positive, it's good. If it's negative, I suppose it's not. Okay, now we'll spend a lot of time talking about this, but again, like the difference between sort of these mathematical idealizations of signals and then the real signals we're actually interested in, right? You have the same situation here, which is to say, again, in your 1,100-page book on signals and systems, you have just lots and lots of talk of signals expanding, decaying, all this kind of stuff, bounded, all this kind of stuff. The truth is that when you end up doing real engineering, you're not interested in these, right? What you're actually interested in quantitative things, like, well, okay, fine to know it converges, that's great. How fast does it converge? How long will it take before it gets below a certain level and stays there? Okay? I mean, to make it quite specific, you take the insides of a current processor, and you imagine a gate inside it driving some other gate. Well, there might be some circuit in between that might model your interconnect or something like that. This is totally irrelevant, right? So, but the point is, here, and this goes into the next gate, okay? The point here is that this one gate triggers, it goes, say, from low to a high voltage, like 0 to 1.8 volts, something like that, okay? And then you know from 101 that after some delay, the signal here is going to be eventually it's going to be this voltage, okay? How long? Well, you probably also, I mean, if I did that, you would for sure know because it's just an RC question. Later in this class, you'll know how to calculate this number. But to make the observation that this signal eventually reaches 1.8 volts, I think, I mean, the way I say it, you can imagine it is of not the slightest interest in practice, right? To have designed part of a processor and have someone come and say, so how does that work? You designed the interconnect there? You go, well, yeah, the signal eventually gets through. Yeah, it converges to 1.8 volts. I mean, nothing could be less relevant, right? Now, here's something relevant. What's relevant is, okay, this signal gets above 0.9 volts, which is the threshold for this gate, in 2.1 nanoseconds. That's really relevant because that tells you that you can do this, say, 450 million times a second. Got it? Okay, so again, it's important to distinguish between sort of these mathematical idealizations and things like that. Okay, so what we're really interested in are quantitative questions. How long does it take for this signal to get above, 0.9 volts? Not abstract things like, oh yeah, it eventually gets there. So, on the other hand, you start with these. Right? So that's the basic idea. Okay, let's see. We're going to start our next topic with. I think we might be. What time do other people have? What time do you guys think it is?
9:49.
9:49, huh? Okay. Okay, we'll look at one more. Unless there's some questions. Yeah, good. I did a whole day and we covered actually no actual material. I was just about to cover some material, but we didn't. So, yeah. So don't think the rest of the class is going to be like this. The rest of the class will actually cover material. So our next topic is going to be impulsive signals, and I don't know. You've probably seen some of this before, but we'll go over it. So, okay. I'm getting all sorts of nonverbal signals from SITN, indicating that the class is over. Right?